So in this video, with the continuity of logical instructions, I am going to explain the next logical instruction as a CMA. So the function of this instruction is a CMA is complement accumulator. So basically by the use of this instruction is going to find out the ones complement of the accumulator content. So now we'll see their opcode first. So the opcode for this instruction is CMA. And as I told you, by default their operand is accumulator content, so no need to mention the operand separately. So that is the part of this instruction itself. So here as a operand we will write as a none. Now we will understand their operation in detail with the example, and then we will see further. So for example, let's say if the accumulator content before execution of this instruction is 89H. So now if we will write this CMA, so this is the data here before execution of this instruction as a CMA. So now if we will write this CMA, then what will happen? This will find the ones complement of this accumulator content. So here this accumulator content we will write it here as a 89H. It means in the binary pattern this 8 can be written 1000 and 9 can be written 1001 in binary. So now we need to find out the ones complement of 89H. So ones complement of 89H will be what? This 1 will change to 0 and 0 will change to 1. So we can write here 0, 1, 1, 0 and again further 1, 1, 1, 0. So here their hex equivalent will be 7 and this will be 6. So after execution of this instruction as a CMA, what will be the output here? So this accumulator content, it will become here as a 76H after execution of this instruction CMA. Now what will be their impact over the flags? So we need to write down this into the note that by the use of this instruction as a CMA, no flags are affected. No flags are affected. It means whatever will be the flags status before execution of this instruction, that status will be carried forward same after execution of this instruction also. So that is the meaning of no flags are affected. And basically this instruction is used whenever we have the need to find out the ones complement of a given data, or whenever we have the need to find out the twos complement. By that time also we can use this instruction. So for example, whatever we have the data, if I want to find out their twos complement, so let's say if this accumulator is having 89H, and whenever we will write this CMA, so after execution of this CMA, this accumulator content will become as a 76H. Now in this one, if we will add 1 to their LSB, then it will become 2's complement of the given data as a 89H. So now if we will write it here as a ADI01H, it means at this place what will happen? This accumulator content will happen 76H plus 01H. So this will become here as a 77H. It means in the binary pattern, if we'll find out here, that is giving the 2's complement of this given data as a is equal to 89H. So this instruction basically used for finding the ones complement of a given number, or even with this instruction use CMA followed by this ADI01H, it is giving here the output as a 2's complement of this accumulator content whatever it has taken. So that is the use of this CMA instruction. Now we'll talk about their size in terms of byte. So here if you'll see that this instruction consists of only English alphabet, there is no operand also. So that is the reason their size will become here as a 1 byte. their size will become here as a 1 byte, and this byte is fetched from memory to the processor, so it is going to access the memory only one time, and that operation is called here as a opcode fetch operation. So due to that reason, their machine cycle will be one machine cycle, which is called opcode fetch machine cycle. Opcode fetch machine cycle, only opcode it is required from the memory, rest of all the things is happening as like accumulator content is inside the processor, then this arithmetical logical unit is also inside the processor. So all these remaining operations will happen inside the processor itself, and the result will be stored into the accumulator itself. So due to that reason, no need to go outside after this one operation. So that is the reason as a machine cycle also it is required only one machine cycle, and as we know that this by default it is called opcode fetch. So for the opcode fetch, by default the number of T states required is 4 T state. So as a T state it will be 4 T states here. And here about the flags already I had given that no flags are affected. So here you need to keep in mind that there is no operand separately mentioned for this instruction. By default accumulator content is the operand here. Then CMA is finding 1's complement. If you want to find out 2's complement, then we have to use that another extra instruction which is called ADI01H. Now it is giving 2's complement, and here after execution of this CMA instruction, whatever is the status of the flag, it is not going to change. So this is also here the key point for this instruction, and then the rest of the part as a size, it is required only 1 byte. Machine cycle is 1 machine cycle. By default number of T states will be 4. So I hope by this way you understand this instruction in better way. Thank you.